the power from the engine of a motor vehicle is transmitted from the differential to the rear axle via a chain drive. The two chain sprockets are of the same size. You see here, there is one sprocket, the other sprocket, they are of the same size. So the chain is not pre-stressed. The chain is not pre-stressed means that the force on the slack side is equal to 0. So we have only a single force on one side of the sprocket, which is the force on the tight side. The sprockets are located on two identical shafts. So these two shafts here are identical. They are both made from the same material, EN23 steel, and the required factor of safety is 4. So factor of safety is given. The material of the two shafts is given. The chain transmits 100 kilowatt, so the power is given at a chain speed of 50 meters per second. So the power is given and the velocity, the linear velocity is given. Normally when the power and the linear velocity are given, this means that we can calculate the force. So the force is equal to the power divided by the linear velocity, okay? So the motor speed is given as well, 6,000 RPM. Find an appropriate shaft diameter using the distortion energy method, distortion energy theory method. Okay, and some dimensions are given here between the sprocket to the first bearing and between the two bearings as well, 160 mil and 40 mil. So if we focus on the top shaft, there is a combined stress state where we have bending and torsion. So the power is given 100 kilowatt. The drive shaft speed is 6,000 RPM. The chain, the linear speed of the chain is given as 50 meters per second. The factor of safety is given as 4, and the material was given. So based on or from this table, we can extract the yield strength of the material, the elastic modulus if needed. In the problem, it says find the suitable shaft size or diameter based on the distortion energy theory. So we go back to our lecture, and then we find the equation for the distortion energy theory. So the diameter is equal to 32 times the factor of safety divided by pi multiplied by the yield strength of the material times root the bending moment squared plus 3/4 multiplied by the torque squared. So as you can see, in order to find the diameter, we need to find both the maximum bending moment on the shaft and the torque on the shaft. The factor of safety is given, it is 4, and the yield strength of the material is given. It is 590 megapascal. Okay, so our task now is to try to find the maximum bending moment and the torque. The torque is straightforward because we have on the top shaft here, for this top shaft, we have the power and we have the RPM, okay? So the RPM is given and the power is given. So it is straightforward because the torque is equal to the power divided by omega. So again, omega is equal to 2 pi multiplied by n over 60. And you see here, it is 6,000 RPM. So n here is 6,000 RPM. Then you can calculate omega, and then the power is given. The power is 100 kilowatt. So in this case, 100 times 10 to the power 3 to convert it to watts. And then you calculate the omega, so this will give you the torque. Okay, so we are done with the torque. The torque is uniform across the shaft. So in order to find the maximum bending moment, we need to first find the force on the sprocket. As I said earlier, using the power and the linear velocity of the chain, you can find the force on the sprocket. So you have a sprocket, And then you have the force here of the sprocket, and on the other side here, just theoretically, you have zero force. So in this case, using the power and the linear velocity of this chain, you can find the force. So the force is known. Now, if you look at the shaft again, let's look at this shaft. So you have bearing here. So we need, let's say, call this A, this B, and this C. So we have reaction force here at A. So we have RA. We have another reaction force here, so RB. And then we have the force here, the force of the sprocket. If we look from the side view like this, so we look from here and then draw whatever you see here, you'll find that you have two sprockets and then there is a chain between them. So you have force here, which is, if we consider this as your tight side. So the force here, it depends actually. Let me just remove this portion and then say, if it rotates in this direction, so the tight side will be here, and then you have the force here. Or if it rotates in the opposite direction, so you have the tight force here. It depends, okay? So let's go back here. So we have, if we have this case on the right-hand side, then in this case, you have the tight side here, and the force is going down. So you have the force at point C here. So you have the force going down. This is FC, or the force on the sprocket. You have a bearing here. You have another bearing here. And then you can assume the reactions. So you have a reaction force at this point. You have another reaction force at this point. This is A. So you can just assume the directions for now. And if the numbers are positive, so it means that your assumption is correct. And then this is quite simple problem, because you have a beam or a shaft here. Then you have one reaction force here, another reaction force here, and you have the applied force at this point. Then simply, if you apply the equilibrium equations, the moments at point A is equal to 0, summation the moment at point A is equal to 0. And if you assume that this is your positive direction, for example, you will be able to find RP. Then apply the second equilibrium equation, all the forces in the y direction goes to 0. And if this is our positive direction, so this will give you RA. So in this case, RA and RB can be found. What about the bending moment? So our target here is to just find the maximum bending moment and then to substitute this value into the distortion energy theory equation. So the bending moment at point A and C are zeros, actually. So in here, this is one end of the shaft. This is the other end. So the bending moment at these two ends are zeros. If you were to calculate the bending moment at point B, so and then you know that when we calculate the bending moment, we focus only on one side. So if you focus on the right-hand side here, so it is like that. This is point B, and this is the force FC, and then this is your point B, and then the distance between here to there is 40. So the force FC multiplied by 40 mel, this gives you the bending moment in Newton mel, or the force multiplied by 0.04. So this is in meter. So it gives you the bending moment in meter. So the moment at C and the moment at A are equal to 0. So the bending moment now is maximum at point A. Then simply here, if you just draw the bending, so this is the bending moment diagram. You see here at this point where this is point A. So this is your point A, this is your point B, this is your point C. So that this is X, and this the moment goes here. So the bending moment is 0 at A, the bending moment is 0 at point C, and then the bending moment is 80 at point B. Going back here, because this force is going downwards, so the deflection the deflection or the bending is in this direction, it goes down in this direction. So is based on the sign convention, this is considered as a negative bending moment. So that's why it is here. It is negative here because of the bending is in this direction. It doesn't matter the direction or the negative sign, because normally we have the bending moment squared here. So either you substitute the value as 80 or negative 80, so eventually you will get the same answer. So this is the distortion energy theory equation based on only we have moment and torque. Then the factor of safety, if it's not explicitly given, so consider this as 2, but here it is given as 4. So the factor of safety is 4. The bending, the yield strength of the material is given as 590. So I go back here and say the factor of safety is 4. This was given. Its yield is 590 megapascal. Then the bending moment. So megapascal here is Newton per millimeter squared. That's why I was saying that I like this combination of units, because it doesn't make any problems. So any forces in Newton, any dimension in mel, any stress or strength or elastic modulus in megapascal. Then you just apply here or just substitute the value of the torque and the moment that we had, and then the diameter of the shaft can be found. Right, so we are going to move to problem number 6 now, where we are going to calculate the critical speed of rotation. So determine the critical speed of rotation for the steel shaft shown here. So first, the diameter of the shaft is given. It's 50 millimeter. The mass of this gear or desk or pulley is given as 50 kilogram. The dimensions of the shaft are given. It's like 600 on each side. And consider that we have 2 bearings here, right? Then the length of the shaft is 1200 millimeter, the total length of the shaft. The shaft diameter is given as 50 millimeter. The mass of this desk in the middle, or this weight is 50, the mass is 50 kilogram. And the Young's modulus of the shaft material is steel. It's 207 gigapascal. Remember, this was the first case in the table that I have shown to you. So the first case says that if you have a single mass in the middle, then you have kind of 2 bearings here, and then the maximum deflection or the maximum value of delta static is going to be in the middle. Okay, so based on this configuration or this beam, you have a central or concentrated load in the middle of a simply supported beam. So if you go to the table that you saw in the presentation, you will find that delta static for this case is W, which is the weight in the middle, multiplied by the total length of the beam cubed over 48, multiplied by the elastic modulus of the material, multiplied by the moment of area. You can find this equation also in the deflection of beams tables. Okay, so what we need to find, what we need here in order to calculate the static deflection, the weight. So the mass is given. Simply multiply the mass by g. So this will give you the weight. Elastic modulus is given. The I value or the moment of area. We have a solid circular shaft. It's pi times d to the power 4 over 64. So this can be calculated easily as well. So the second moment of area is here. We can calculate it. It's 307 times 10 to the power negative 9. This is in meter to the power 4. Okay. Then W, which is the weight in Newton, it is the mass multiplied by G. So going back here, so the mass is 50 kilogram. So you just multiply here 50 times 9.81. So this gives you the weight in Newton. Then go back to this equation, substitute all these values to get delta static. Remember the N critical in this case is equal to 30 over pi multiplied by root G over delta static. So G is 9. So 30 over pi times root G is 9.81 divided by delta static, that is 0.278 times 10 to the power -3. This will give you the critical speed of the shaft as 1793 RPM. Okay. This is quite simple, but it is quite important as well case, because normally even if you have more than one mass, you have to use the superposition method, where you will consider one mass at a time. And then if you consider one mass at a time to calculate either the deflection at each point or to calculate the critical speed for each case, you might need to do something similar to this. Problem number 7. You see here we have interesting problem. We have a converse system employs an assembly of belts. So we have a pulley here, we have another pulley here, and it just converts or transmits the power through a belt. So the belt and the chain, they are quite similar, but there is one significant difference between them. For example, if you have a shaft here, okay, and then there is a pulley, right? And then you have another shaft here, okay, and it has a pulley as well. And then you wanted to convert or transmit the power between them using a belt, okay? So the belt goes around the pulleys like this. And then if this shaft rotates in this direction, so this shaft is going to rotate in the same direction. Of course, you can use a smaller pulley here, larger pulley here, just to increase or decrease the speed, etc. Okay. The idea here is that when we use this kind of configuration with the chain, we said that we have a tight side and we have a slack or loose side, and the force on the loose side is equal to 0. But here, when we have this belt, so the case is different, because we have force on both sides. So we have force here, we can call this F1, for example, and then we have F2. And F1 and F2, they are both positive, so it's not equal to 0. So they both have values. In this case, the torque that is here, so of course you have here opposite and equal forces. But if you focus here on the left-hand side pulley, you have a pulley here, and then you have a force F1, another force F2, and then you have here a pulley with a specific radius R. So the torque eventually is equal to F1 minus F2 times the radius, where F1 is greater than F2. So you choose the higher force first. Then I'm not going to make a derivation here, but the idea is that if you, for example, focus on force F1, then say I'm gonna add here at the center, add two forces, like F1 in this direction and F1 in this direction. Then this force F1, I didn't do anything here. I've just added two equal forces and opposites. So if you focus on this force and this force, these two forces are equal, and there is a specific distance between them. So they make a coupling, right? Then again, you just say for this force here, F2, I'm going to do something similar. I'm going to add F2 here, and then I'm going to add F2 here, and then this force and this force, they have a specific difference or a specific distance between them. So these two forces, they make a coupling. again, so you have two couplings now, one coming from F1, which is F1 multiplied by R in this direction, and another coupling that is based on F2 that is in this direction, which is F2 times R. So the difference between these two couplings, or the difference between these two torques, gives you the net torque on the shaft, okay? So that's why I say here the torque is F1 minus F2 times R. It is like if you call this T1 and you call this T2, so the T1 is equal to F1R and T2 is equal to F2R, then the torque T is equal to T1 minus T2. So this is how you calculate the torque if you have belts, okay? We have two pulleys here and we have two torques actually, but they are equal because the power is transmitted between these two pulleys without any losses. So we have the same shaft, so it has the same speed. So if the power is constant, the speed of the shaft is constant, so the torque must be constant as well. So let me just remove all this and then try to read the problem again. So what we have here, guys, we have a conveyor system employs an assembly of belts. The belts have tensile forces applied as shown, and the shaft is located with frictionless bearings. So we have two bearings here, bearing A and bearing B, at locations A and B. And this is the first pulley where we have, as I said, force F1, F2, and then this is the radius, 0.075 meters. We have another pulley at point C where we have force F1 and force F2, and the radius is 0.050 meters, okay? So these are the two pulleys that we have, and these are the forces and the bearings, okay? So what is required now? The yield strength for the shaft material is given. So we know that the yield strength is 500 megapascal. Factor of safety is given. Determine the smallest shaft diameter based on the distortion energy theory, the maximum shear stress theory, and comment on the answer. So what we have here, we have a combined stress state. But what is interesting about this problem is that we have eventually here, we have forces in this direction and we have forces in this direction. So we have forces in two perpendicular planes. So we have here horizontal plane, and then we have forces on the vertical plane as well. So we need to kind of solve this problem in two different planes and then use the Pythagoras theorem to find the bending moment at point C and B, as you will see. So as I said, if you consider that this is x-axis, okay, and then this is y-axis, and then this is z-axis, good. Then this is the location of the pulley on the right-hand side. This is the location of the bearing. This is the location of the pulley in the middle. This is the location of the bearing on the left-hand side. So as I said here, if you go back, so you will find these two forces. They are in the horizontal direction. When you move them to the center, where you have this torque, so these two forces, they add together and then they become 500, okay? So you see here that we have in this horizontal direction or XY plane, we have here 500 Newton, okay? In this case, we are going to have a reaction force at this, a horizontal reaction force at this point. Let me just, so it's A, B, C, and D. So we have A here, okay? Then we have B, we have C in the middle, and we have D here, okay? So you will have a horizontal reaction force at B, another horizontal reaction force at A, okay? So reaction force at A, this is in the horizontal direction, reaction force at B in the horizontal direction, okay? Then if we look at this pulley here, you will find that you have a force going down, which is 950. So in here, we have a force that is going down, it's 950. This force is in the vertical plane. So this means that we should have here a reaction at point B, but in this case, it's going to be in the vertical plane. We have reaction here at point A, which is going to be in the vertical plane as well. Remember that when I was talking about the pulleys, this one and this one, I said that we have torque here and there, and I've shown you how to find the torque. So the torque in this case is going to be for the first pulley, it's going to be in this direction. And for the second pulley, it's going to be in this direction. If I go back, just consider that the torque goes with the higher force. So the higher force is here at the top. So this is going to be in this direction. And then the higher force in here. So the torque is going in this direction. That's why I'm just showing them like this. And if you follow the equation, F1 minus F2 times the radius. So this means that the torque here is going to be 7.5 Newton meter. And then here again, it's 7.5 Newton meter. We have the distance between point B and D, between B and C, between A and C. So the idea here is that you focus on one plane at a time. So we have a plane XY, and then we have another plane XZ. So XY is our horizontal plane, and XZ is our vertical plane. Okay, so this is what we are going to do. Now, the torque is known. So as I said, the torque is known. It's F1 minus F2 times R, but the bending moment is unknown. So we need to focus on the bending moment. Once you find the bending moment, we know the torque. So I can go back to the distortion energy theorem and the maximum shear stress theory to calculate the diameter of the shaft. Okay. So you see here on the right-hand side, we have here the vertical plane. So we have X here, okay, and then the vertical plane was Z. So here is the moment in the Z direction. Then on the left-hand side, we have XY plane. So XY plane. So this is the moment in the Y direction. Okay. So in the horizontal plane, as I said, we have here a force that is 500 on the right-hand side pulley. And then there is a reaction force at this point, another reaction force at this point. These two reaction forces, it's RA horizontal and then RB horizontal, okay? So this is very simple to calculate. So you can calculate RA, just focus on this side only, the left-hand side, and then consider that you are just studying a beam that has a force going up 500, and then try to calculate the actions based on the equilibrium equation. Then go to the right-hand side here where you have one force, 950 going down, and then calculate the reaction force. Let me just change color. So you have a force going down here, 950. Then you have a reaction force at this point. It's reaction force at point A in the vertical direction. You have a reaction force here at point. So the reaction force here RB in the vertical direction. Then once you find the reaction forces, it is quite simple to find the bending moments, okay? So if you look again at the left-hand side, the bending moment at point A is equal to 0. The bending moment at point D is equal to 0, and you can see them on the graph here. So you need to find the bending moment at point C and the bending moment at point B. The bending moment at point B is quite simple because in here you focus on the right-hand side only. So it is 500 multiplied by 0.15. And then the bending moment at point C, you consider the two forces on the right-hand side or the one force on the left-hand side. By now, you would have calculated RB horizontal. In this case, it is being calculated, it is 650. Then multiply this 500, multiply this 500 by this distance, and then multiply the 650 by this distance to calculate the moment at point C, which is going to be 37.5. Then, so we have these two moments here in the horizontal plane. So this is horizontal now, and then this is the vertical plane. So you can calculate the bending moment at these points because we don't have any forces here, so the bending moment is 0. And at this point, on the right-hand side, you don't have any forces, so the bending moment here is 0 as well. And then in order to calculate the bending moment at point C in the vertical direction, so you multiply this reaction force RB in the vertical direction by this distance, which is 0.25. So it's going to give you the bending moment here. Then you want to combine them now together because they are perpendicular. One is vertical, one is horizontal. So you say, okay, where is the worst point? Where is the worst point here that has the maximum bending moment? So I have two major points actually. So or two, if you remember yesterday, we were talking about the critical section. So we are now trying to identify the critical section. So at this point, and the corresponding point, we have two moments, one in the vertical direction, one in the horizontal direction. But at this point, we have one moment in the horizontal direction, but the moment at the vertical direction is equal to 0. So it just means that point C for us is the critical point, okay? Because when you add these two together, so it becomes the critical point. So the bending moment based on XZ plane, which is the vertical plane, is 118.75. The bending moment based on the XY plane is 37.5. So how you add these two together, you should use the Pythagoras theorem because you have here two bending moments perpendicular to one another. One is the bending moment in the horizontal direction, the bending moment in the vertical direction. So it is added like this, okay? So now the torque is equal to the force multiplied by R. So it's F1, F2, and here is the radius, or F1, F2, and here is the radius. So this is for one pulley, and this is for the second pulley. And as I said, power is the same, omega is the same, torque should be the same for the two pulleys, okay? Because the same shaft rotates with the same speed, no losses, so it transmits the same amount of energy, so the torque should be the same, which is 7.5. So the torque is known now, and based on the previous slide, the moment at this point C is known. So you can use the distortion energy theory, factor of safety. Let me just go back here. Is it given to us? So the factor of safety is 2. Okay, so the factor of safety is 2. Yield strength of the material is given 500. So this is the yield strength 500. Factor of safety is 2. The torque is 7.5. And then the bending moment, if I go back one step, it is 124.5 Newton meter. So substitute all these values here to come up with the diameter of the shaft. Or based on the maximum shear stress theory, we have here another equation. These two equations are quite similar. There is only one difference. You will just notice now. If I just get rid of these, you will find that everything is the same apart from the torque. So the torque here is 3/4, and the torque here is 1, multiplied by 3/4 here and multiplied by 1 here. But here, if you calculate the diameter based on the maximum shear stress theory, so again, you will have the same diameter. Why? Simply because if you compare the value of the torque to the value of the moment, you will find that the value of the torque is quite small. It's 7.5 compared to 124.5. So the equation is not affected too much by the value of the torque. That's why they both lead to the same diameter. So for the last problem here, what we have a 50 millimeter diameter shaft, okay? 50 millimeter diameter shaft is made of high carbon steel, okay? The yield strength of the material is 380, okay? And locates a spare gear of the same material, right? So the diameter of the shaft is given 50 millimeter. The material of the shaft is given, carbon steel, and we know that the hub here is for a spare gear, okay? And it is made of the same material as the shaft, which transmits 300 Newton meter of torque. So the torque value here is given as 300 Newton meter. Okay. Design a suitable square key. So the focus here is going to be on the key. So the diameter of the shaft is given, and the amount of torque that is going to be transmitted is given 300 Newton meter. The material of both the shaft and the hub are given, and then here design the key in which mode of failure is the key most likely to fail. Okay, we have two types of stresses. Okay, the first type is for shear. Okay, and then we have a square key. So for a square key, we have the width as W and the height as H. And then we said that it is recommended to have the width is around 1/4 of the diameter of the shaft, okay? And because we have a square key here, so both the height and the width are going to be 1/4 of the diameter of the shaft that is given, okay? So here at this portion, it just shows the shear area. So the shear area here is W multiplied by L. Here, if you look at this graph, so it is this area here. This is the shear area, where here is W and the length is L. So L multiplied by W is your shear area. Based on that, so the design shear stress is less than or equal to the yield shear strength of the material divided by the factor of safety. The 0.5 times the S yield is the yield shear strength of the material. The factor of safety is 3 for the key. So in this case, this gives you the design stress, or the right-hand side of the design equation. The left-hand side of the design equation is the force divided by the area shear. So this is the calculated shear stress. So the calculated shear stress here is the force divided by the area of shear. So the force, remember the torque was given. So the force is equal to 2T divided by D. Okay, or the torque divided by T or D over 2. So the torque is given, the diameter of the shaft is given, so we can simply calculate the force, right? And the area, so this is the area of shear. It's equal to W times L. So substitute this into here, substitute this into here. So you'll end up with the force divided by area shear is equal to 2 times T, 2 times the torque divided by the diameter of the shaft, times the width of the key, times the critical length of the key. So the variable here is going to be the critical length of the key, because the diameter, the width and the height are known now based on this assumption here. So in this case, the torque is known to us. The tau design, which is the right-hand side of the equation based on the factor of safety and the material properties, is known. We've calculated this already as 63.3. The diameter of the shaft is given, and the width is 1/4 of the diameter of the shaft. So this gives us a critical length of the key as 15.16. So the key length should not be less than this value in order to avoid failure due to shear. The second and the last part is due to compression or bearing stress, we call it. So again, we have a square key. So the height and the width are equal. They are equal to D over 4. In this case, the left-hand side is the calculated bearing stress, which is the force divided by area bearing. or the compression area is equal to the yield strength of the material divided by the factor of safety. Yield strength is given 380, factor of safety is 3, so this part, the right-hand side of this equation is known. The left-hand side, so we have the same force. Again, it is based on 2 times T over D. And the area here of bearing, if I go back here and then remove this shear area and then say the bearing or the compression happens between the hub and the hub and the key in here, this area here, or between the shaft and the key at this area. So it is the top half of this key. So it is H over 2 times L. This is the area bearing, okay? So in this case, so the area bearing is H over 2 times L, okay? So substitute this value here and then substitute the value of the force. So it gives you 4 times the torque divided by D, which is the diameter of the shaft, times the height of the key, times the L critical, which is the critical length of the key. Again, so we're trying to find the critical length of the key based on the compressive or the bearing stress. So L critical here, if you just rearrange this equation, so L critical here is equal to 40 times the tau design, which is 126.7, multiplied by the diameter of the shaft, multiplied by the height. Remember, the height is equal to D over 4 because we have a square key. So in this case, we have the same, exact same value for L critical. So designs are equally robust in shear and compression if the same material is used. It is worth remembering this. So remember that if you have the same material for both the shaft and the hub, so either you design your key based on shear or design based on compression, it's going to give you the same length. But it is, again, every time it is worth checking that you design based on shear and then you design based on compression, and then you choose the larger length